Yes, sir.
Yeah, thank you. So last class we have seen about some of the devices like short circuit plunger, wave guides. Okay, so then we have seen some 1 minute. Yeah, waveguide we have studied, and we have seen some different types of waveguides with the respect to their modes, and which mode is called as the dominant. Okay, so the mode with the lower cutoff frequency. Okay, already told about the what is the difference of lower cutoff frequency and higher cutoff frequency. So we required both the component. Actually, lower cutoff frequency is also required, higher cutoff frequency is also required in general communication system. So in day-to-day life, we are using our mobile phone. Okay. So how we are getting the signal with the mobile phone? So once the frequency matches and the impedance matches, and also the power is going out. Okay, power is dissipated or transmitted in terms of radiation. We cannot able to see in naked eye. So through measurement device, we are acquiring the what is the information going in terms of the matrices alone. But through naked eye, we cannot see. Suppose two users are there, mobile users are there. Okay, so when they are transforming some information, how we can see in free space the information, whether it may be a text data, whether it may be audio data, whether it may be a video data. We cannot able to see what is the data they are sending in the free space spectrum. Okay, so it is in real. Okay, we cannot able to see through naked eye, but through simulation softwares we are seeing how the signal is going, and how it can be animated. We are seeing in the synthesize tool or simulator. Okay, so students, if any of them are waiting outside, please let me know. Yeah. So in the different types of modes, we have studied about the three different basic types of the modes are there in electromagnetic spectrum. Actually, this spectrum has been defined by the Maxwell's equation. I hope you have you know this term you have studied in your physics in your 12th, Maxwell's. So the Maxwell is the scientist who defined how the spectrum property has. It has both the electric and magnetic field. Both are transverse with each other. The word transverse is nothing but perpendicular to each other. Okay. So based on that only, the that is divergence and the curl has been expressed in dot product and the cross product. This also a mathematical max concept you have studied. Okay, so anyway, that concept is not required here. Okay, just you know that what is meant by a transverse electric, what is meant by transverse magnetic, what is meant by the transverse electromagnetics. So this is the basic modes is followed in your microwave component. You can see how the test, you can see it is in a vertical mode. It is not positioned an horizontal. Okay, so your length component is tilted in this direction. It is in perpendicular with respect to the ground plane. How the mode is going, you can see it is differentiated with the two colors. One, maybe I don't know which color is represent for electric and which color is represent for magnetic. Just for two understanding purpose, here the color variation is there. Okay, maybe I am considering blue is your electric field and whereas orange is your magnetic field. So both two are transverse with each other. So as I told, the dominant mode we will look it up. So why we seeing the dominant mode? It is the lower cutoff frequency. So in the case of transverse electric field, you can see TE10, magnetic field TM10, and transverse electric magnetic, you can see TEM10. These are the dominant mode. So when come to the cutoff, what is the cutoff? Suppose I want to see the average of our class. So in which way I can able to see the average? So suppose I am conducting the test to you. So around some 29 students are there here. So whatever mark you have attained, I will add sum of all the marks divided by 29. So that is my averaging of my class. Okay, that is my averaging of my class. So if I want to know the class percentage, okay, that is pass percentage, not class percentage, pass percentage, then what I have to do? Out of 29, how many of them cleared? Okay, that is to suppose there is four failures are there. Example only I am telling. Our students are brilliant. Everyone will get a good mark. We will get 100%. Okay, so in example I am telling some four failures are there. So then how can I evaluate my class pass percentage? It is 25 divided by 29 into 100. So that is my class percentage. In similar here, we are finding the out of that spectrum, what is my cutoff for that particular wavelength. Then I am there is a two entities are there. Mostly, please see here. There is a one terminal is for your input and other terminal for your output. So I am dividing by two. Okay, I am dividing by two. So you can we can make it as a three also for three port network or four port network, etc., etc. So that is a different things. Okay. So this is nothing but your electromagnetic field based on your wavelength. So when I'm averaging, it will become the lambda c by 2. Okay. So apart from this, we are going for some depth parameter. What all the parameter calculation can be done. So there are five basic parameters over there. One is the cutoff frequency, then the cutoff wavelength, then phase velocity, or dominant mode, and guided wavelength. So before getting into these formulas, just formula is there. Okay, just know about these that is formulas. Mm, okay, so what is the cutoff frequency is that out of the two out of the two um, frequencies, that is lower cutoff frequency and higher cutoff frequency. Okay, we are averaging of two and we finding at 3 dB point. At the 3 dB point, what is your cutoff frequency? Similarly, the cutoff wavelength also. Okay, similarly, the cutoff wavelength also. So in cutoff wavelength, we are suppose I am having the wavelength around some 10 centimeter or 10 meter. Okay, at the zeroth centimeter or meter, what is the value of the gain? And at 10th centimeter, what is the value of the gain? Okay, so then I have to average it off and I have to do the further calculations. Okay, so that is called as the cutoff wavelength. The next one is the phase velocity. So what is the phase velocity? Actually, everyone know about what is meant by velocity. Velocity is nothing but the rate of change of acceleration. Okay, the rate of change of acceleration. Okay, so that is nothing but your velocity. So where the phase is nothing but what is the phase is nothing but when the two signals are going simultaneously and it will have some interference. Suppose some input signal, my voice is the input signal. Along with that, some fan noise or then some audio noise coming from my home. So that both together is combined to this mic, and you cannot able to clear my voice in clear. Okay, so the two signals are coherent, and it becomes an interference to that output side. Okay, then same way the phase velocity also. The velocity is nothing but a rate of change of acceleration, but it is nothing but how the phase component comes. Okay, and a dominant mode, as I told, what is meant by a dominant mode? Dominant mode occurs at the lower cutoff frequency alone. What is the guided wavelength? Suppose, so in the waveguide, which is your guide, the waveguide system only. Okay, so there have some protecting medium inside the holograph only, gap only. It is the signals are propagating in terms of radiations. So for that, they will find out what is the guided wavelength also. So the formulas alone given, just I will show it off. So for phase velocity, can see phase velocity is denoted by V suffix P, C divided by root of 1 minus Fc divided by F whole square. So where C is nothing but a real velocity. Okay, real velocity. So this velocity component, you can see this velocity component is very higher than that. That is, sorry, it is equivalent that of the rate of velocity of light. So everyone aware about what is the velocity of light? It is 3 into 10 to the power 8 meter per second. So it is equal. Okay, so I can tell the phase velocity is directly proportional to the velocity of the light. Okay, so once the impedance match with the critical frequency and the operating frequency, you can see in denominator there is a two frequency component has been given. One is the FC. FC is nothing but a critical frequency, and F is your operating frequency. If two are matches, then your velocity rate will be getting fixed. Okay. Similar also, in similar, the guided wavelength. You can see the guided wavelength also given. The guided wavelength will be equivalent to the wavelength of your spectrum or the waveguide. Okay, so the lambda divided by root of 1 minus fc by f the whole square. There is some specifications are there whenever we are seeing in your workbench, that is microwave workbench. We have to look into the what is the accuracy of the system, how efficient the system will be work, whether the attenuation is less in your system, and it is directivity. Directivity is nothing but what the point the that is the two point of view. Okay, that is two systems are there. So if I am aligned according to the, suppose the two best, that is example I will tell, and the two persons are standing before, that is with some distance, they are talking. Okay, so one person is talking and other person is listening, but the third person in the other direction, maybe in left side or the right side of the who is listener, so they also disturbing that person who is listening. Okay, so then what happened? So he will turn back and he will listen to that. And if suppose the right person is talking, he will listen to them. And ultimately, he cannot get what the person who is talking continuously before to him. Okay, so then I can tell the point of view is not properly aligned. Okay, so the directivity is poor. So in a general communication system, the transmission line should be properly aligned with alpha with respect to the transmitter and receiver. Then only we can get the high directive gain. Okay. And the last one is ability to carry the high frequency. Okay. So suppose this point I will correlate with the same example. If the two persons talking, okay, so only these two alone, they are talking continuously. They not listen others one. Then I can tell they are able to carry their high frequency. There is no power dissipation at all. Okay, they are not deviate with the other person's talk. Okay, they two of them only continuously talking, and they have the full concentration with the two of them alone. Okay, they not bother about the other person. In similar way, if the the system is concentrated within the two entities like the transmitter and receiver, okay, then it not bother about the intruder what signal is coming on. Only the it able to carry the high signal. Okay. So this already I have explained to you. Isolator. This is the device and this is the component which is available in our laboratory. There are many companies who are fabricating this isolator device. So this is you can see some Ferranel. Okay, Ferranel. Okay, so this is the one of the company which is fabricating and manufacturing this type of device. You can see at both the side you can have the some holes are there, four holes are there, which is for to connect the two, and that is which for connecting the devices. Okay, so this is the vernier caliper setup for setting up the reading with help of the coaxial connector. You can see the CMC has been mentioned. So this is one of the type we have seen in our coaxial connector also. There is a two ports are there. You can see one port will be have male connector and another port have the female connector. So like this, the setup has been given in the general block diagram. So you can see at one port it will allows the black color indicates that it will allow, where the white arrow mark is denotes that there have many filters are there. You can see one big filter and somewhat moderate size and another one is very small. It not allow. Okay, so this blocker will not allow the signal in the other direction. Only unidirectional device. It is isolator is the unidirectional. Okay, I already told it is a uniline. Okay, so this is provides the minimum attenuation and it is very high attenuation in opposite direction. So which means that in opposite direction, more noisy signal will come. Okay, that won't allow to that system. So what only this system we used the frequency stability. Okay. We can tell it as a frequency stable device also. This type of unit will be used in the microwave generator. Okay. So and also you can see other ports, only two port network. This is a two port network. So I can tell the third and the fourth port are with the matched load, or else I can tell it is closed. Okay. So this is the isolator device. You can see it is a two non-reciprocal. Okay, so I told when we seen the waveguide concept itself, I told that two types of devices we have studied. One is reciprocal, another one is non-reciprocal device. Okay, non-reciprocal device. In that, what we studied is that. Okay, what we studied is that. That is, there are several devices we have seen. Under the non-reciprocal device, only two types of devices we have seen. One is isolator and another one is circulator. Okay, so this isolator device is used to prevent the possible reflection from the damaging the source. Okay, so that is it not allows. Okay, it not allows the reflection. Sometimes it leads to some bulky beam voltage also. It leads to some damage to the device. So what only this type of isolator will be there in your microwave gadgets. So here more heat energy will be produced. Okay. So based on the different types, you can see there are different types of isolators are there like resonance absorption isolator, field displacement isolator, and Faraday rotator isolator. So actually in our syllabus we are studying about the Faraday rotator isolator. Okay, Faraday rotator isolator. You can see the Faraday rotator isolator. You can see there is two vanes are there on input side and output side like resistive vane, and in between you can see the some Faraday rotator will be there. Okay, so how the signaling is goes with respect to the input signal, incident signal, and how come the some reflection is going back. and what is the progressive phase shift is adding. Okay, so sorry. You can see when the signal is enter into the Faraday rotator. Okay, so it will be in a zero phase shift only first. Okay, it will be in a zero phase shift. Then when it enter into the next vein, it will have additional progressive phase shift of 45 degree. Okay, and again when it enter into the output waveguide, it will self match with the 45 degree. So like that, 45 degree additional progressive phase shift will be added till it comes to the original position. So this is due to the Faraday law, okay, or Faraday rotator. The Faraday rotator is basically manufactured or fabricated with the help of the ferrite material. This ferrite material is in proper produce the proper phase shift, progressive phase shift. Okay, so this is the working mechanism as per this construction diagram. Okay, so I already told in the last class about some of the microwave engineering apps are there. Okay, so I hope since everyone aware about the Play Store app, so just to put it microwave engineering or RF engineering or antennas, etc., whatever it may be. Don't take the textbook. This is one of the textbook, but we want some of the apps like this. Okay, so you can find. I will give some time for the assignment after your that is first internal overs. Everyone have to do any one component alone. You can take it. You can see there are many things are there: microwave, power measurement, insertion, PSWR, crystal detector, etc. Any one alone, please take it, and please take the snapshot of it, and then you can see some buttons will be there for setting your input operating frequency, wavelength, and after that if you simulate means you can get a real time how the signals come in simulated manner. You will get the thing. Okay, so you can take any one of the app, not this app itself, microwave engineering. For sample I am showing to you. You can use any tools also. Okay, so now you are using the Sonnet software for your electromagnetic lab. Okay, so there are some other softwares also used for designing this 3D model of the microwave device, and we can able to we can synthesize that device, and we can able to see the simulated output also. Okay, so in last class, this thing also we have studied, that is rectangular to circular waveguide. You can see in a three-dimensional mode. Okay, in a three-dimensional mode, you can see one of the rectangle is positioned in the three-dimensional space. Okay, but the device is like this in real time. Please see that the device, the picture has been given like this. One end will be a rectangular waveguide, in other end will be the circular. So I already told which is the dominant for the rectangle and which is the dominant mode for the circle. So that is TE10 is your dominant mode for the rectangle and TE11 is for your circle. So this is the way TE10 to TE11 or TE11 to T0. So when I'm conversion, please see how it can be converted. This is one of the best animation you can see. From the origin, it will be looks the borders and the corners of that boundary of that given rectangular cuboid. Okay, so when it push, it will be bend. It is somewhat bended, and please see some of the curve position for the inner boundary and the outer boundary. It will be calculated the coordinating system, and please see, and the coordinate system will be in a circularly polarized. Okay, circular manner the field component has been calculated. Okay, and then please see this diagram. Okay, so just to see, this is one of the thing how it can be geometrically it can be proven. Okay, geometrically proven. please see this is one of the circle which has the area as the pi r square and the perimeter will be 2 pi r. So when I am cutting the first half and it becomes the triangle. Okay, please see the triangle. When cutting the two things, it becomes one rectangle. Okay, so that is pi r square. Okay, so just see this is one of the thing. It is converting geometrically, converting from the rectangle to the circle or circle to the rectangle. I hope this conversion the basically done here also, but we are mainly focused on the signal propagation will be the dominant mode alone. Okay, we're not mostly concentrating on the geometry, but we looking on the dominant mode, that is minimum cutoff frequency. What is the wave is passing over to this guided medium. Okay, so that is what we need. Okay, I hope you have understood. So the next one is the phase shifter. Okay, the phase shifter. The phase shifter component will be available in most of your microwave passive device also. It is also a two-port passive device that produces the variable change in phase of the wave transmitted through it. Okay, you can see here also the rotator, same rotator will be there. You can see there is a three different categories are been mentioned in the below diagram. That is input lambda by 4 plate, rotatory lambda by 2 plate, and output lambda by 4 plate. So you can see when the input signal at the one terminal, okay, so it will be in a sinusoidal. Then when the additional signal is sorry, when it enter into it, some progressive signal also goes inside the medium. That is literally called as some reflected wave. Okay, so when it comes, it will be progress. You can have. I am considering our input signal in one axis, x-axis. In y-axis, some a reflected signal will be there. When it go inside the medium, okay, across to the rotator, it will goes like this only. With the progressive phase shift will be added along with your input signaling, and it leads with some velocity. Okay, so depends of our operating frequency, the signal rate will be varies. Okay, whether it may goes slow or whether it may goes in moderate speed or whether it may go to the high speed. Okay, so this is what the signal will be propagate in terms of radiation inside the phase shifter component. The next one is the attenuator. Okay, attenuator is also the same, but you can see this is one that is as of now we have seen all are the rectangular waveguide. So just to see the waveguide wall, one wall alone. In the wall, you can see some of the observer will be there to observe the sound or some observe the heat, etc., etc. So some input signaling comes from the input port, and when it strike on that wall of the waveguide, it becomes the reflected wave. Okay, reflected wave. That wave will be added with the same self reflected signal itself add, that leads to some heat energy that will be add continuously with your system, and it leads to the some signaling. So what only you can see this third point I have used designed using resistive film. So what is the resistive film is that it is for the observer. Okay, it is used for the observer to send the power without any dissipation. Okay, so there is the two types of attenuators are there. One is fixed attenuator and another one is variable attenuator. So what is the fixed attenuator? The fixed attenuator at one side up to one particular direction alone we can able to we can position that attenuator. Okay, so this is also used to absorb the power. It is a very thin dielectric material. Okay, it is at a room temperature only it conduct. It will be along or merge along with the waveguide wall. Okay, waveguide wall, and it results to observe the attenuated power. Okay, so it will be like this only. The setup will be like this. So the dielectric strip is tapered at both the end up to the length of more than half wavelength to reduce the reflections. Okay, so this is one of the thing we have used, and you can see the resistive vane is supported by the two dielectric rods separated by a odd multiples of quarter wavelength and perpendicular to the electric field. So what they're telling is that if it is tapered, okay, if an attenuator flap is tapered like this, then it will have separated with the odd multiples of quarter wavelength. That is lambda by 4 of that particular waveguide should be there, and it should be perpendicular to the wavelength. Okay, so the amount of the power in the fixer attenuator can observe, it will be observed. That will be depends on some certain matrices or performance measures like strength of the dielectric field and the location of the power observer film. Then we should know what is the area of the film. Then we should know what is the operating frequency. Then what is the material used for that observer. Okay. So the next one is the micrometer. The micrometer is a one used in the variable attenuator to have the tuning of microwave power. So actually, in a microwave meter, mostly this device will be incorporated with any of the device. Not only with your variable attenuator, it will be in a VSWR also, or it may be in a slaughter line section also. It is like a vernier caliper setup. It can be tuned in terms of VSWR or meter or centimeter, etc., etc. It may be in analog or it may be a digital, whatever it may be. So that is based on the maximum attenuation and based on the depth of insertion, the micrometer can be adjusted with the variable attenuator. So this is called as the variable attenuator. The same device will be available in our laboratory also. Mostly in the microwave setup, this type of device will be used. So this attenuator flap can be rotatable and we can vary according to our. I can see at that is the figure number B can have one knob to rotate. So once we rotate that thing, the resistive film can be accordingly positioned so that the point of view may be changed with respect to input and output. Accordingly, the attenuator